Hello students, welcome to lecture 6 of atomic structure. Now our topic is evidence for the quantized electronic energy levels, atomic spectra. When an ordinary white light passes through a prism, that white light split into a colored bands called spectrum. So this is the ordinary white light and this is the prism. When this ordinary white light passes through a prism, split into colored bands. So these are the colored bands. It is called spectrum. When ordinary white light passes through a prism and this white light split into the colored bands called spectrum. We know that the colored band is VIBGR. VIBGR. V is a violet and I is a indigo and B is a blue and G is a green and Y is a yellow and O is a orange and R is a red. And this VIBGR range is 400 to 750 nanometers. And the violet color has shortest wavelength and red color has longest wavelength. Violet has shortest wavelength and red color has longest wavelength. And the spectrum ranges from violet to red is 7.5 into 10 to the power of 14 hertz to 4 into 10 to the power of 14 hertz. The spectrum ranges from violet to red. From violet to red. The range is 7.5 into 10 to the power of 14 hertz to 4 into 10 to the power of 14 hertz. And here in this spectrum, the violet merges into indigo and indigo merges into blue and blue merges into green, green merges into yellow and yellow merges into orange, the orange merges into red. Then such a spectrum is called continuous spectrum. So this spectrum is called continuous spectrum. And see here, this is the lower energy level and this one is the higher energy level. At lower energy level, there is a atom or molecule and this is the electromagnetic radiation. So when electromagnetic radiation interact with atoms or molecules, then the energy will absorb and they can excite it to higher energy level. So this atom or molecule excited to higher energy level. Now atom is here at higher energy level But at higher energy level, these atoms or molecules are unstable, so they can come back to the lower energy level by emitting the radiation. Now, this atom or molecule emit the radiation and come back to the lower energy level. So this atom emit the radiation. Then this atom come back to the lower energy level. This emitted radiation will give the spectrum. So when electromagnetic radiation interact with the atoms or molecules, and energy will be observed, then the atoms or molecules are excited to the higher energy level. At higher energy level, these atoms or molecules are unstable, so they can emit the radiation and come back to the lower energy level. This emitted radiation will give the spectrum. Here we have two spectra. One is the emission spectra and another one is the absorption spectra. Let us discuss the first one, emission spectra. This is the diagram for emission spectra. It is an excited sample, that is atoms or molecules or ions. And this is the prism, and here it is a film. On the film we can see that spectrum. We know that with GR range (400 nanometers to 750 nanometers). This is the wavelength. So the atoms or molecules or ions observe certain wavelength of radiation. When heat the sample, the observed radiation emitted and will give a spectrum with the remaining wavelengths as a dark space in the spectrum. If you see the emission spectrum, so here this is the color band and here it is a dark space, and this is the color band. And this is the increasing wavelength. So the atoms or molecules or ions observe certain wavelength of radiation. When heat the sample, the observed radiation emitted and will give a spectrum with the remaining wavelengths as a dark space in the spectrum. So here, from here to here, this range observed by the atoms or molecules or ions, and when you heat that molecules or atoms or ions, that observed radiation will be emitted. That emitted radiation will give the color band, and the remaining range of wavelength will appear as a dark space. So the spectrum of radiation emitted by the substance that has observed called emission spectrum. Next one, absorption spectra, and this is the diagram for absorption spectra. And this is the light source, and this one is the sample, and it is a prism, and this one is the film. And here atoms or molecules or ions observe the certain wavelength of radiation, and the remaining wavelength of radiation will give a spectra with observed radiation as a dark space in the spectrum is called absorption spectra. So if you see that absorption spectra, so here this is the dark space. This observed wavelength of radiation as a dark space, and the remaining wavelength will give the color band, and the remaining wavelength of radiation will give a spectra. This is the color. So atoms or molecules or ions observe a certain wavelength of radiation, and the remaining wavelength of radiation will give a spectra with observed wavelength of radiation as a dark space in the spectrum. It is called absorption spectra. So these emission and absorption spectra called line spectra or atomic spectra. So these emission and absorption spectra are called line spectra or atomic spectra. And here this is the increasing wavelength. This is about emission spectra and absorption spectra. Now let us solve some problems. The problem number 1.1 in the textbook. Calculate the number of protons, neutrons and electrons in bromine 3580. Calculate the number of protons, neutrons and electrons in bromine 3580. Let us solve this problem. So here the atom is given, the atom is bromine, and here the subscript is 35 and the superscript is 80. We know that superscript indicate the mass number and subscript indicate the atomic number. So here Z is equal to 35 means atomic number 35, and A is equal to 80 means the mass number 80, and this space is the neutral space because there is no charge, there is no negative and no positive, so it is a neutral atom. And we know that the number of protons is equal to number of electrons in neutral atom. So here number of protons is equal to number of electrons. Number of electrons. Number of protons is equal to number of electrons. And we know that formula to find out the neutrons. Number of neutrons is equal to mass number minus atomic number or number of electrons, means Z, is equal to A is the 80 minus Z is equal to 35 is equal to 45. We know here number of protons is equal to number of electrons is equal to atomic number. So atomic number 35 and number of electrons also 35 and number of protons also 35 because it is a neutral atom. So in the question, we have to find out that number of protons, number of neutrons, and number of electrons. So here number of protons is equal to number of electrons is equal to atomic number, that is 35. So number of protons is equal to 35, and number of neutrons is equal to A minus Z is equal to 80 minus 35 is equal to 45. So number of neutrons is equal to 45. And next, number of electrons is equal to atomic number. That atomic number is 35, or number of electrons is equal to number of protons. So number of protons 35 and number of neutrons is equal to 45 and number of electrons is equal to 35. Next one from textbook, the problem number 1.4. The wavelength range of visible spectrum extends from violet to red. The violet is at 400 nanometer and red at 750 nanometers. Express these wavelength in frequencies edges, and 1 nanometer is equal to 10 to the power of minus 9 meters. Let us solve this problem. First of all, we are taking the frequency of violet light. Frequency of violet light. And we know that wavelength formula lambda is equal to c by mu. So here we know the velocity and we know the wavelength. So we have to find out that frequency. So we can write that mu is equal to c by lambda is equal to velocity of light is 3.00 into 10 to the power of 8 meter per second and divided by the lambda given 400 nanometer. 1 nanometer is equal to 10 to the power of minus 9 meters. So we have to take in meters. So 400 into 10 to the power of 9 meters. Then if you do this calculation, we will get 7.50 into 10 to the power of 14 hertz. So this is the frequency of violet light in hertz. And next one, frequency of red light. Same formula, wavelength lambda is equal to c by mu. We need mu is equal to c by lambda. So velocity 3.00 into 10 to the power of 8 meter per second and divided by wavelength of red light 750 nanometers. So 750 into 10 to the power of 1 nanometer is equal to 10 to the power of minus 9 meters. So 10 to the power of minus 9, 10 to the power of minus 9 meters. So if you do this calculation, we will get 4.00 into 10 to the power of 14 hertz. So this is the frequency of red light. So the range of visible spectrum is from 4.00 into 10 to the power of 14 hertz to 7.50 into 10 to the power of 14 hertz.